Hello and welcome to my channel, Rhino here. Today we're looking at a rather small channel that I was made aware of by David Hummer. This dude is tiny, so while I am leaving a link to his video in the description, I would ask that you not dogpile his channel. He seems like a nice enough guy, and if you really feel the need to comment on his video, please be respectful. I do not want to be the reason why another creationist channel switches off the ability to comment on their videos. We've got enough like that, let's not make another one. Anyway, Trinity Vandenacre is here to tell us about carbon dating, and he does it in a very roundabout way, so I will be cutting a bunch of clips of him hiking and making coffee and stuff like that.
There's this barbed wire fence in the groin.
So let's take a look.
Just to warn you, this might get a little technical, but I'm gonna try to make this a little more human friendly, because a lot of times this scientific stuff is just stated in a way that makes it impossible to understand, and I feel that's probably on purpose so that you don't ever really look too closely at the dating methods that the scientific community uses to date fossils and the earth.
Starting off strong with some conspiracy thinking. Yeah, the reason scientific research is highly technical is so that nobody can understand it, obviously. No, scientific stuff is highly technical because science is highly technical. You're using a pretty advanced camera setup there. It is highly technical. I'm a bit of a hobby photographer when I have time myself. Did the camera manufacturers make their cameras highly technical so that hobbyists like me wouldn't be able to understand it? Or is it maybe just that the art of capturing images can get highly technical? And I'm just talking about using the camera here. I'm not even touching on how the camera itself actually works, and all of the technical knowledge that goes into it there that photographers don't even need to have a cursory understanding of. I'm just talking about things like white balance, ISO, depth of field, aperture, shutter speed, composition, histograms, and how all of these things interact with each other. And that's not even touching on any post-processing that you might want to do, like color grading, making composites, adjusting black levels, shadows, saturation, vibrance, using the tone curve, applying lens corrections, and so on. I suppose these are all just highly technical things that are there to prevent me from understanding how to take good pictures, right?
First of all, there's a terrible misconception about radiometric dating that I've found just by posting videos on TikTok and YouTube and things. People tend to confuse radiometric dating all as one single thing, which it is not.
Correct. Well done. Usually it's the creationist confusing them as one homogeneous item. But yeah, there are different radiometric dating methods which are used in different scenarios. For instance, uranium series dating would be used in older samples, and carbon dating would be used on younger samples. And if you want to know why radiometric dating is so complicated, let me just give an extremely oversimplified summary of how uranium series dating works. There are three radioactive isotopes involved in uranium series dating: uranium-238, uranium-235, and thorium-232. Uranium-238 decays into lead-206 and helium. Uranium-235 decays into lead-207 and helium. And thorium-232 decays into lead-208 and helium. All of these decay chains that lead to different isotopes of lead have different half-lives, and the ratio of uranium-238 to uranium-235 has been calculated to be 137.818, and using this ratio, and the fact that these decay chains all result in different isotopes of lead, we can figure out how much of each isotope of uranium was originally in the sample, and thereby calculate an age for the sample. This is very different from rubidium-strontium isochron dating, which I go into more detail in my video on different dating methods. And both of these are very different from carbon dating, which we're going to get into in a moment here. So yeah, all the radiometric dating methods are different, and the differences run a lot deeper than just a simple matter of looking at a different atom.
There are several ways to do radiometric dating, and they're not all equal.
No, they are not all equal. They have different error margins. Uranium-lead is actually one of the most accurate methods. And they have been regularly checked against each other, so one sample will be dated using several different dating methods. Usually these methods will agree with each other. If they do not, then it suggests that there might be a problem, and other methods are used to determine which age is accurate for that particular sample. But I know you're going to get into carbon dating, so let's just skip ahead to that.
In radiocarbon dating, you have an isotope that's created by the atmosphere, in the atmosphere, by the sun, by the rays of the sun. And it slowly decays away after something dies. So you're testing how much is left in the animal.
Okay, that explanation was a little bit mangled, so let's clarify. Carbon-14 isotopes are created by the interaction of cosmic rays with our atmosphere, producing neutrons. These neutrons are then captured by nitrogen-14 atoms, replacing one of their protons and turning them into carbon-14. The carbon-14 will then interact with oxygen to form carbon dioxide, which will then be absorbed by the organisms living on the planet at the time. Once an organism dies, it stops absorbing carbon-14 from its environment, so the amount of carbon-14 it does have will diminish as it decays back into nitrogen.
So we can measure, supposedly, we can measure the rate at which it's decaying and come up with an age.
No, the decay rate has been measured independently several separate times, so we don't just measure the rate at which it's decaying and then use that to come up with an age. We measure the ratio of carbon-14 to carbon-12. An uncalibrated date and a calibrated date are then calculated from this ratio. The uncalibrated date is just the simple calculation of how long it would take for enough carbon-14 to decay to give the ratio that we find in the sample, when compared to what the starting ratio would have been given today's ratio of carbon-14 to carbon-12 in the atmosphere. The calibrated date uses a calibration curve that is used to figure out what the actual ratio of carbon-14 to carbon-12 would have been when the sample was formed. The production of carbon-14 in our atmosphere is not a constant, but it is measurable up to about 50,000 years in the past using methods like dendrochronology. The possibility of contamination also has to be taken into account, but I feel like you won't be too worried about that, as the result of contamination of a sample will be to make that sample appear younger than it actually is, so contamination would actually give dates that are closer to being favorable to your position.
Until more recent times, carbon dating worked like this. You would test how much carbon-14 was in your subject or the object that you're testing, and then you would see how much C14 is in the atmosphere, and you would use that as kind of a starting point. Like, it had that much in it when it died, and then we test now how much it had in it now and use the rate at which it's decaying into nitrogen, and that should be able to give you a formula to figure out the age.
No, they've always been using a ratio, and while carbon dating did start out without the use of calibration curves, older data has often been re-examined as we improve and refine the calibration curve. So is that what you're referring to?
But that is kind of breaking down recently. So they're using a ratio now. What they're doing is they're using the amount of C12, which is supposedly completely stable in the atmosphere. It is a stable isotope.
No, that's not how it works. Stable does not mean that the levels are all the same. So what they're doing now that apparently, according to you, they weren't doing before, is directly measuring the amount of carbon in the atmosphere in the past through dendrochronology, which is actually relatively simple. Take a core sample, figure out the ages of different rings, and directly test those rings. Living trees are not pumping modern carbon into old rings, and the date of the old rings are known through non-radiometric methods, and so they can backward calculate how much carbon-14 was in the atmosphere in that specific year by looking at the ratio of carbon-14 to carbon-12 in the ring and applying the half-life calculation to determine the amount of carbon-14 that would have been in the ring when it first formed. The same is true of dead tree rings, and as the patterns of tree rings living in the same area will match up with each other, the tree rings on dead trees can be compared and dated using living trees, and then these older dead trees that now have known ages can be used to date even older trees, and so on. We have an unbroken record of dendrochronology going back about 11,000 years. We can go back even further by combining different dating methods, but 11,000 years is how far back we can go with just the tree rings. And using the data from these tree rings, we build the calibration curve. And even aside from the calibration curve, the first test of effectiveness of carbon dating was performed in 1949 using samples of known ages ranging from 900 to 4,900 years old without a calibration curve. This experiment confirmed that before even the development of the calibration curve, radiocarbon dating was reasonably accurate up to 4,900 years. But later testing did reveal some discrepancies that were coming back with ages that were hundreds of years off from what they were expected to be, which isn't a lot when speaking geologically, but we're talking about human history here. A few hundred years is a long time as far as humans are concerned. So it was determined that calibration curves were needed. The first calibration curve was developed in 1967 and covered a period of about 9,000 years. And coming from dendrochronology, these calibration curves, the most recent one published in 2013, are using data that can give us specific carbon levels for exact years. So yeah, I guess back in the 1940s they did just assume carbon levels were all the same, but that was never an assumption that sat well with scientists, so they developed methods to accurately and directly measure carbon levels.
but they're saying that it's always constant, that the amount of C12 is always the same in the atmosphere.
Nope. Nobody has ever said that. They may have started with the assumption that the ratio of C14 to C12 was constant, but even from the beginning, that was not an assumption that scientists were happy with, which is what led to the development of the calibration curve. As far as I know, nobody has ever claimed that the actual carbon levels have remained constant. In fact, it's not hard at all to find graphs that have been put together using dendrochronology and ice core data to map out carbon concentrations in the atmosphere over time. Here's one going back 800,000 years. Scientists have known about the fact that carbon levels are not constant for at least 124 years now, and realistically, probably a lot longer. That was just where the connection between global average temperatures and carbon dioxide levels was first laid out.
The ratio of C14 to C12 is 1 trillion to 1, meaning for a trillion atoms, 1 trillion, you heard me right, 1 trillion, for every trillion atoms, I need to say that a bunch of times, there is 1 atom of C14. So for a trillion atoms of C12, there's 1 atom of C14.
Yeah, that's the approximate current ratio. It's super tiny. We know this. That's why carbon dating usually requires such big sample sizes, anywhere from 10 to 100 grams. You have to make sure that whatever you're sampling will produce enough of a signal to be distinguishable from background noise. And that's assuming you're using the cheaper liquid scintillation counter machines rather than an accelerated mass spectrometer, which are so precise that you can actually count the individual carbon atoms.
Because science is not accurate enough if you think about how little amount of C14 we're looking for here. So let me give you a word picture of really what this looks like, okay? And something that your mind might be able to grasp. Talk about water. So 1 drop of water is measured as a metric drop, okay? And there's 75,000 drops in 1 gallon of water. How much water would you have if you had 1 trillion drips of water? You would have over 13 million gallons of water. So think about this. You have 13 million gallons of water, and in that 13 million gallons of water, you are looking for 1 drip, a specific drip that's different than the, I don't know how many drips that is because we're talking gallons here.
Okay, but remember, we're dealing with atoms here. There are a lot of them in very small spaces. 12 grams of carbon contains 6.02 times 10 to the 23rd carbon atoms. If 1 out of a trillion atoms are carbon-14 instead of carbon-12, then there are 602 billion carbon-14 atoms there. And they are radioactive, which means they emit detectable radiation. So to fix your analogy, which I haven't checked the math on, so if it ends up being wrong, don't blame me, you've got 13 times 10 to the 18th gallons of water, and you're looking for 602 billion individual water molecules, which are glowing at you. Still not an easy task, but it's doable.
If you have a trillion atoms of C12, and you miss 1 atom of C14, meaning you think there's 1, but you miss 1 of those other drips in there, you have doubled the amount of C14.
Correct. If you're dealing with a small enough amount that 1 single atom would be the only one left. This is exactly why there are minimum sample sizes. In order for 1 missed atom to make a significant difference, you'd have to have sample sizes 1,000 times smaller than what we're dealing with here. So instead of 10 grams of, say, charcoal, you would need 0.01 grams. That's 0.00035 ounces for you Americans. Oh, also, fun fact, that's exactly the kind of sample size you would need for accelerated mass spectrometry, on account of the whole being able to count individual atoms thing. So generally, the larger the sample, the more accurate the number will be, because missing 1 or 2 individual atoms will have a much smaller effect on the final calculation when the numbers are larger. Think of it this way. If 1 person in 100 is wearing a red shirt and everyone else is wearing a blue shirt, then if you go out and meet 10 people, odds are you won't find a single red shirt. You just missed it. If you write a report on shirt color based on this experience, you will come to an erroneous conclusion. But if you go out and meet 10,000 people, then you'll probably have around 100 red shirts in your report, and would come to a much more accurate number. The law of large numbers ensures that the larger your sample size, the more accurate of a representation your final result will be. Same thing applies for counting up carbon atoms. Yeah, if you're looking at a sample size that having one single carbon-14 atom go missing would massively skew the results, your results will be less accurate. That is why that not only do the different methods of figuring out how much carbon-14 there is have minimum sample sizes, it's also why carbon dating is not reliable on samples that are older than about 50,000 years. So yeah, you can give ridiculous analogies all day about how hard it would be to find one single carbon atom if you only had 1 trillion atoms of carbon to work with, but at the end of the day, that is never the scenario that we are looking at. It's always a large enough sample size that missing a few atoms here and there won't affect the outcome. So in our 10,000 people analogy, maybe you only found 99 red shirts. You still come up with 0.99% of the population in red shirts, which is close enough to 1% as to make no functional difference.
You're talking 1 trillion to 1. This isn't a ratio of 3 to 4 or 1 to 1 starting out with. This is an astronomical ratio to begin with. And to try to measure something like this and then say that you're going to get an exact date and be fully confident with that is just plain ignorant.
I mean, aside from the whole law of large numbers thing that I went over earlier, we've also checked it against things that we do know exact dates for, with margins of error in the single digits. And it has been reasonably reliable. Sure, for recent history there are other methods that will get you closer to an exact date, but we're talking tens of thousands of years here. Also, just a fun note, if the dates are wrong because we're not seeing carbon-14 atoms that are there, then that would mean the dates we are getting for these samples are too young. So if your argument is that we're missing a bunch of carbon-14 when we take our measurements, then the results that we get will show them as being younger than they are. So when we carbon date a sample to being 20,000 years old, that would make the real date, 25,000 years old? This argument does not help your case. And next he lists a bunch of assumptions that you have to make in order for carbon dating to work, so let's skip his preamble and head straight to his list.
You have to assume that the ratio to C12 and C14 has been the same for the amount of time that you're measuring.
Nope, that is not an assumption that we make. Calibration curves are a thing, and before they were a thing, scientists did make this assumption but did not like it. They just hadn't quite figured out how to test it yet.
You have to assume that carbon-12 was exactly the same as the carbon-12 in the atmosphere at the time of the object's death, because it only works on something that was living at one time. What I mean is the plant, you have to assume that the plant has the exact same amount of C12 in it and C14 in it that the atmosphere does right now when it died.
Well, here's a graph showing the carbon levels in the atmosphere for the last 50,000 years, with the present being on the far left and 50,000 years ago being on the far right. Since this data was available after a few seconds of Googling, I'm going to go ahead and assume that scientists performing carbon dating are aware of this and take it into consideration when calculating their dates. In fact, it's probably built into the calibration curve.
And without a time machine, you cannot tell that.
Nope. We have ice cores and tree rings that allow us to tell that, both of which allow us to directly measure the atmosphere in the past. No time machine necessary.
Another assumption is that you have to assume that the rate at which C14 breaks down into nitrogen has always been the same, regardless of the outside influence.
That's not an assumption. That has been tested repeatedly. Nothing is known to affect radioactive decay rates, at least not anything we're likely to see in nature. If you accelerate carbon atoms to significant fractions of the speed of light relative to us, then that would affect our measurement of their decay rate, but that doesn't strike me as a likely naturally occurring phenomenon. And then there's also the fact that the different dating methods have been used to corroborate each other, so if the rate of carbon-14 decay changed at some point in the past, it correlated with a change in the rate at which ice sheets develop layers, and how many tree rings grow in a season, and the decay rates of other atoms, and how quickly electrons can escape from electron traps for ESR dating, and more. So all of these independent dating methods would have had to have undergone severe and undetectable changes in their fundamental processes in completely different ways, but in a way that would make them give false data that is in complete agreement with each other. That's just not a reasonable thing to think.
That is a lot of assumptions.
No, that's 3 assumptions, 2 of which you just reworded and doubled up on, which I skipped. And all 3 of them are assumptions that are not actually assumptions. They are either repeatedly tested and measured, or they are variables that are adjusted for when calculating ages.
So if any one of those assumptions is off just a little bit, your date does not work.
Correct. hence the existence of calibration curves. Also, the fact that decay rates are frequently independently measured to make sure they are correct rather than just using the known number.
Something that is 65 million years old, like the dinosaur fossils, even though they were living once, should have 0 carbon-14 in them.
Not quite. With technicalities about how half-lives work, it will never actually reach 0. But it will be close enough as to make no difference to us, so it will have effectively 0 carbon-14. But that's also based on the assumption that no new carbon-14 will be produced, which is not always the case.
We continually find carbon-14 in dinosaur fossils.
Yep, correct. Remember earlier when I explained that carbon-14 is made in the atmosphere when nitrogen interacts with cosmic rays? Well, a similar reaction can take place in fossils and minerals as the result of interactions with other radioactive particles. Remember, the C14 isn't just disappearing when it decays, it turns into nitrogen. Other radioactive materials nearby can interact with this nitrogen to turn it back into carbon-14. It's not something that happens with enough frequency for it to affect the dates given for samples within the 50,000 year limit for carbon dating, but it is enough to produce measurable amounts of C14, because we can measure the amount so precisely nowadays. This is part of the background radiation that is accounted for when scientists use carbon dating to determine the age of a sample. It's also a creationist favorite. Send a 65 million year old fossil in for carbon dating without telling the lab what kind of sample it is, and loudly proclaim that carbon dating doesn't work when it comes back with the wrong age based on this background radiation.
They always cry contamination every time C14 is found in one of these items. Here's my question. If carbon dating is so easily messed up by contamination that every time we measure anything that is supposed to not have carbon-14 in it but does, it's actually contaminated, then why in the world are we using it as an exact dating method?
Because we know how the contamination happens, and we can measure the rate at which it happens by measuring the radioactivity of the rocks surrounding the sample. So it is entirely possible to account for contamination caused by these nuclear interactions when dating samples that are within the appropriate age range for carbon dating.
Carbon dating and coming up with a 50,000 year limit is determined by the fact that the assumption that the amount of carbon-14 in the atmosphere and the amount of carbon-12 has always stayed the same. But has it? Because one of the things that many scientists today never take into consideration is the sun and our magnetic field and what they do to the Earth. They were some of the biggest forces that we know of.
I'd really like to know where you're getting the idea that scientists never take those two things into consideration. I remember back on one of my first videos dealing with carbon dating, one of the first things I found when researching it is that the amount of carbon-14 produced in the atmosphere fluctuates based mostly on the strength of the magnetic field, but also with solar activity.
And yet they're hardly ever used to determine anything. If you look at the magnetic field, the stronger the magnetic field is, the less particles of C14 that are created in our atmosphere.
How did you determine that, I wonder? Did you figure it out for yourself, since scientists seem to be completely unaware of this fact? And also, scientists do take this into account. Once again, calibration curve. Fun drinking game idea. Go back through this video, watch it again, and do a shot every time I say calibration curve as a response to this guy not understanding that calibration curves are a thing. Try not to die of alcohol poisoning.
There are far more dating methods than science actually acknowledges or uses. One of which is like the moon. How did the moon get there in the first place? That's an interesting thing because things don't get captured by the Earth's gravity and stay in orbit. They fall into the Earth or they just are flung outward.
What? The existence of the moon is a dating method because you don't understand how orbital mechanics work? Not sure where you're going with this one.
Moons just don't form, okay? I can demonstrate that, and if you want to see a video on that, let me know.
Yes, oh my god, please, yes. I would love to see you demonstrate how moons cannot form, while simultaneously living in a solar system that contains at least 181 moons.
It's kind of interesting. Anyway, the moon is moving away from the Earth at 1.5 inches per year right now. Now, here's one place where evolutionary scientists believe that speed at which it's moving away from the Earth had to vary, because otherwise it would be sitting right on top of the ocean about 1 million years ago.
Incorrect. We know that the speed does vary, but that's because the configuration of the continents has changed. But if we assume it were a constant, it is currently 384,400 kilometers away. So at 3.8 centimeters per year, or 1.5 inches, it would have had to have been 1,012,000,000,000 years before getting to the actual surface of the Earth. If the speed had remained constant, the moon would still be well outside the Roche limit 4.5 billion years ago. The Roche limit is the distance at which tidal forces would rip it to pieces. The Roche limit for the Earth is about 18,237 kilometers. 4.5 billion years ago, if the rate of recession were constant, the moon would be 171,000 kilometers closer to the Earth than it is now, leaving it 213,400 kilometers away. That's still more than 195,000 kilometers away from the Roche limit.
There's also dating methods right now that especially the evolutionists are attempting to use, which is ice cores, counting the layers in the ice cores and counting the rings on trees. Very, very unreliable dating methods, and I can actually spend a little time on those and might make a video on one of those if somebody is interested in that.
Well, call me interested and make your video. I'd love to know how you consider them to be unreliable, especially considering that there are literally dozens of different ways to date ice cores, and they all tend to be in high agreement with each other. That's it for today. Today's comment of the day comes to us from Ejnar Sorensen, who says, "We are still part of our ancestral taxa, so whales are fish after all." I'm hoping this was a joke because I did explain it in that video. Fish is not a monophyletic term, with monophyletic being a grouping of organisms that all share a characteristic trait like vertebrates having vertebrae. Fish is a polyphyletic term because the way it is defined does not include all the descendants of the most basal fish. So we are not fish, and whales are not fish, but we are still part of whatever monophyletic clade also includes our common ancestor with fish. So thanks for watching. Special thanks to my patrons, who are the screeching noise that keeps the dial-up modem that is my show going. If you'd like to screech at me, you can support the show at patreon.com/ViceRhino for as little as $1 per episode. Or for one-time donations, a PayPal link is in the description. You can also follow me on Twitter at ViceRhino, or find my Facebook page, website, and P.O. Box address in the description. See you next time!